Next speaker is Rasmus, who's going to tell us about a verified pipeline for compiling, I suppose, from a specification language to Rust.
Yes,
please.
Thank you for the introduction. So yeah, I'm Rasmus, a first-year PhD student at Aarhus University, and I did my master's degree in mathematics and learned about Coq about a year and a half ago. And obviously I was intrigued, particularly for the potential of using formal methods for cryptography, which is why my research focuses on that. So let's get into it. It's reasonably common knowledge that in cryptographic code there are bugs that are far too numerous and also potentially very critical. And it is for this reason that a number of projects recently are using formal methods to verify cryptographic code. And this project, although being in many ways still work in progress, is one of those. So what we do is we feature this novel approach of verifying optimized code against specifications written in a specification language.
Excuse me, Rasmus, I don't know if it is on purpose, but you're still seeing your very first title slide.
Yes, this is on purpose.
Okay.
Okay, so more concretely, what we want to do is first of all, we want to verify the code that we produced, which means supplying machine check proofs, Coq proofs of memory safety properties, as well as functional correctness. We do this in a way that is general enough that the methods can be used for a variety of different cryptographic primitives. Of course, abstraction in Coq helps toward this goal, and also our use of code synthesis allows us to do this in a way that we don't have to sacrifice performance too much, hopefully. And finally, an important point is that we want to verify against executable specifications written in this Hacspec specification language. So this is in contrast with what is still the common approach of writing specifications for cryptography in pseudo-code. And having these executable specifications hopefully will help towards narrowing the gap between theory and practice, using specifications that are closer to what implementers would actually write. So in achieving this goal, there was some sound. So in achieving this goal requires some stitching together of different projects. So let's just look at the different parts of the pipeline first. No, this is not what I'm doing now. So just to make sure we're on the same page, what is this Hacspec language? Many of you may not be terribly familiar with it. So Rust is something that many of you hopefully are more familiar with, a programming language that combines features of high and low-level languages. And the C-like aspects of Rust makes it particularly useful for cryptographic applications. And Hacspec is a subset of Rust that don't deal with the low-level stuff, so it's not possible to write highly optimized code, but rather make a point of supporting high-level abstractions. So ideally, you would write your specifications in Hacspec. That is what it is developed for. And we will verify optimized code in Rust against these specifications. So the different parts of the pipeline that I was about to talk about earlier. How do we achieve this goal? We stitched together a number of different projects. One of them is Fiat Cryptogrphy, which compiles high-level Coq code initially to an internal representation, which can then be printed to a number of languages like C, Rust, bedrock, to name a few. Fiat Cryptogrphy manages to produce highly efficient code by using partial evaluation. So I'll point out at this point that even though this compiler does target Rust directly, that is not what we will be doing, because we want our code to make use of things like loops and function calls, which is not directly supported by Fiat. So what we opt for instead is to target this bedrock 2 language. And just to be sure, this is not the same bedrock systems that we heard about earlier. I don't know that there is any relation between these two projects. So what bedrock 2 is a framework that contains an embedded low-level C-like language, this XPRIMP language that lives inside Coq, and also has a formalized semantics and linear separation logic that allows us to reason about programs written in this language. The next part of the pipeline is a Coq-backend for Hacspec, the specification language, which translates functions in Hacspec to Coq. And it is similar in style and structure as other existing backends for Hacspec. There's one for F* and one for EasyCrypt. The final part of the pipeline is our as of yet unverified Rust printer, which translates functions written in this XPRIMP language to actual Rust code. So these are the things that we need to make this work. Let's have a look at how these different parts fit together. Usually what you would start out with is a specification written in Hacspec, and then use the Coq-backend to compile this to functional specifications in Coq. The next thing we do is use Fiat Cryptogrphy to synthesize a number of low-level functions in XPRIMP. And then we can use those low-level functions to write by hand the functions that we actually need and prove those correct against the specifications derived from Hacspec. Once these proofs are done, we can print the XPRIMP functions to Rust. So this is how the pipeline functions in theory. We've done a case study to see how things unfold in practice. We implemented 2 elliptic curves, the BLS 12381 curves. And in case you're not terribly familiar with elliptic curves, all you really need to understand at this point is that they are some mathematical objects, some algebraic objects, which are defined over fields, in our case, finite fields, which can be either prime order fields or extensions of prime order fields. So there are 2 curves in our case study, one that is defined over a prime order field and one that is defined over its quadratic extension. So when I say that we want to implement these functions, concretely what we want are Rust functions that implement for the fields, the field operations, multiplication, addition, and so on, and for the group operations, addition and inversion. So to get an idea of how and what we actually prove about these functions, I've included a relatively simple example, the specification of addition in this quadratic field extension. And it looks like this. Now, I'm aware that there's a lot of text on this slide. Some of it is boilerplate, and I'm not expecting you to read it all, but let's have a look at what's important here and try to digest that. So we're reasoning in separation logic, which means, among other things, that we have a precondition. You'll notice in this precondition, there are 2 things that stand out. One is this valid predicate, whose argument is a list of Coq's integer type, and it simply requires that this list of integers can in fact be interpreted as a list of 64-bit integers that will fit within 64-bit registers, and that the list can be actually interpreted as a number in the prime order field. The other part of the precondition is this predicate on memory. You'll notice the separating conjunction. Thankfully, Joseph just introduced separation logic, so everyone knows what this means and how to interpret it. And big num is essentially just an array. So we require, when calling this function, that there is a number of arrays separated in memory. And similar to the precondition, there's also a postcondition. You will see the valid and big num in the postcondition as well. And other than that, there is this part, the functional part of the postcondition, which for this particular function is this fp2 add Galena spec. So this looks a lot more like something a regular Coq user can easily read and understand. And it's this functional part that we prove to be equivalent to what is derived from Hacspec. So this is one example of one of the functions. There's quite a lot of these, and I won't show you them all because they look more or less like this. But let's have a look at what the diagram we saw earlier looks like for this particular case study. We write in Hacspec the functions that we need, the prime order field operations, the extended field operations, and G1 and G2 are subgroups of the two elliptic curves in question. We then use the Coq-backend to compile these to functional specifications and use Fiat Cryptogrphy only for synthesizing the base field operations here. The rest, which use function calls to these, are written by hand in bedrock 2. And then we prove that these are correct against the specifications derived from Hacspec. And finally, we print this to Rust. So a note on this printing to Rust. Of course, it would be wonderful to have this final part of the pipeline verified as well, but this is a non-trivial issue. And there are a number of challenges that arise when thinking about this. We're really still on the drawing board with respect to this. One thing is that the exprint language, the domain language of this translation, is not a type language. There's just one type, a 64 or 32-bit word, whereas we want to make use of typing information in Rust in the produced code. Also, as far as I know, there is no precise agreed upon semantics of Rust. And doing this translation and verifying it would require us to decide on a proper subset of Rust to be a target of translation, which is not clear what that is supposed to be. There are safe Rust is a possible candidate, but there are reasons to use unsafe features of Rust as well. Fortunately, we are not the only ones who are interested in formal verification of Rust. There are other projects dealing with similar issues. One notable one is Rust Belt, which models a variant of a mid-level intermediate representation of Rust. Of course, targeting this model is not particularly helpful. Targeting this model of when translating is not particularly helpful because we want to actually produce running surface level Rust code. But if and when the project matures to the point where it is connected to something that is closer to surface level Rust, it might be very helpful. So that was just a bit of a side note on the printing to Rust. Returning to the case study, what did we actually learn? For one, we learned that we could actually implement these two different curves in about 5,500 lines of code. And performance-wise, we measured the field operations to be about 80% slower than other unverified Rust implementations. So what do you do with a number like that? You can put 80 in front of it, put only in front of it to make it look impressive. But just to put it into perspective, recently a formally verified implementation of field inversion was picked up by Mirage OS, which is more than twice as slow as its unverified counterpart. So there are reasons to be optimistic about these results. So that is what I had to say. Let us quickly recap what we went through. We introduced this methodology of verifying optimized code against specifications written in an executable specification language. And we did a case study to show that this is in fact feasible. Let me know if you have questions or comments.
All right, thanks, Rasmus.
Thank you.
Are there any questions?
I don't
Maybe
see
in the room, yes?
I don't see any.
All right. So maybe I can ask one question about that 80% slower that you said. What do you think you can do about that? Can you make it? You already said that it is probably good enough, but how would you try to improve it?
So it's something that we are currently investigating. Where does it come from? So there are at least two things that we expect are causing this. And one thing that we did is try to compare what even just the base field operations, when these are synthesized from Fiat. Let me get this diagram. The base field operations, when we synthesize these from Fiat, we can target either Rust or Bedrock and then print the Bedrock to Rust. And there's some degradation, not the entire 80%, but some of it comes just from going through Bedrock as an intermediate step. So why exactly that is slower, that might be a problem with the printer or with the compilation to Bedrock. The other part is that's more of a hypothesis really than a claim at this point, is that it can be caused by how Fiat works. So in order to avoid using a separation logic, Fiat generates a very big number of variables when synthesizing code. And it can be, this is our hypothesis, that this is in conflict with the Rust compiler somehow.
I see. Thanks. Any other question or comments? All right, then let's thank Rasmus again. Thank you.